It is part 2 of section 2.3, short-time Fourier transform. In the first part of the section, we studied the discrete Fourier transform. We implemented it in MathTalent. Also, we discussed the Nyquist criterion, and we understood that only the first half of frequency components is useful and reliable. Here we'll apply the discrete Fourier transform. The short-time Fourier transform is used to analyze how the frequency content of a signal changes over time. Here is the procedure for computing the STFT. First, we divide the signal into short segments of equal length, and then we compute the discrete Fourier transform separately on each short segment. So it is a simple application of the discrete Fourier transform. The magnitude squared of the STFT is known as the spectrogram, which is a time frequency representation of the signal. The short-time Fourier transform requires to set an analysis window G of n of length m. So you have to choose a parameter m, and also you have to select a window G. And also, you have to set a parameter r, that is a sliding length. The window hops over the original signal by r segments. In this case, the overlap L must be m minus r. Most windowed functions taper off at the edges to avoid spectral ringing. That means the magnitude of G becomes smaller toward edges. The discrete Fourier transform of each windowed segment is stored into a complex valued metric of this many columns. Here, n sub s is the length of the original signal. Let's see this picture. I copied it from MathLab information website. This is the original signal having capital N as samples. Now, in the beginning, we choose m samples. So here, we choose from here to there, m samples, and multiply this window function. Here, this is a shape of a hat, and multiply window function, then we'll have this signal. And after moving all samples, that's all movement. Now, here, we are moving from this one over there, so that's R. So same here, R is this one. After moving R, now from this one, we take m samples again, then multiply G, then we can get this signal. We keep going, and then at the last moment, we take m samples around the end and multiply the window function G, and we can get this signal. For each of these signals, we apply discrete Fourier transform. Then the frequency components, the magnitude squared, will appear as in this portion. For this one, the frequency is low, so that you can see the peak in low position of the frequency. And for example, for that one, frequency is high, so that you can see a peak on high position. And peaks are higher gradually, as we can see here, the frequency becomes higher, 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 right? So this will be collected, and each one will make a column, and this whole collection is called the spectrogram. Okay. The STFT is easy to implement. Of course, MathTalent and Octave has the built-in function, but we'll try to implement detail here. First, we have to select an analysis window. I chose such window when m is 150. It is gotten in this way. Now I named it window cosine. The reason is I'm using cosine function. First, select the point from 0 to 2 pi, here m points, and then here by using cosine, we try to get the window function. Here 0.55 minus 0.45 and times cosine t, so that when t is 0 or 2 pi, then there'll be 1, so that the quantity becomes 0.1. So here at edge points, the value is 0.1. Of course, at the center, the value is 1. Okay, that's the window function. Now this is the main part of short-time discrete Fourier transform. Here we start with sampling frequency 10,000. Now capital T0 is 1. And for that one, now time vector can be made in this way. From 0 to 1, we select here 10,000 points. For that, now we try to make a so-called the chop signal. That is now for sine function here, this is increment of the time. Now we put here extra components that represents the frequency increase. In the beginning, the frequency will be 100. Now, when t becomes 1, the frequency becomes the addition of these two, which is 4,000. Okay, this small portion of chop signal is now duplicated 3 times for the data. So x0, x0, x0. So we'll deal with this one. The corresponding time vector is this one, but it's not necessary in our computation, so I commented out. Now we choose m is 150, that is window length. So from this one, by calling un cos m, we get g, that is exactly that one. Now the sliding length r is 60, and here by using the signal and window and sliding length, and we call STFT2 to get frequency components, and is the magnitude squared is spectrogram, and below is for plotting. Okay, let's see this one is implemented here, quite simple. And x is the signal, g is the window function of length m, and r is sliding length, and f is the short time discrete Fourier transform. And first we measure the length of the signal, and m is the length of the window, and here L is the overlap, and we compute the columns for the spectrogram, and that one came from here, that one, the integer of this ratio, and it decided the number of columns. Okay, here. So we open the initialize the array for metric for frequency components and m rows and this much of columns. Okay, now the column is 1 for the first column. Now once so that from the signal we'll try to take the m signals from n0 to n1. So in the beginning, for first column, now n0 must be 1, but for later on, n0 will be moved in all samples, and n1 is always same as n0 plus m minus 1. Okay, after taking m samples, we multiply g, so that becomes the signal, and using discrete Fourier transform function, and its transpose is now saved into the column C, and we make C increased by 1. Of course, you can use for loop, and C is moving 1 to that column. Either way, you can implement this portion. Okay, here, after passing that one, we have these frequency components. In MathLab, we have STFT function. Here, along with 2, I try to separate from the built-in function. Okay. Okay, let's see here the plots. We try to save only the first 1,000 samples of the chopped signal, and in second figure we try to save the Yundong function, and finally now here we try to save the spectrogram. Okay, so that's the first 1,000 samples of the chopped wave. And here the frequency is 100, and now once it becomes 1 second, so that later the frequency will become 4,000. It's oscillatory faster, and later on it becomes 4,000. This 3 copies of this chopped signal is attached for our test signal. Okay, so you can see here the spectrogram for each second start from 100 and then becomes 4,000, 100, 4,000, 100, 4,000. Only the first half of frequency components is useful and reliable, and the second half must be discarded in most analysis along with this transform output. Okay, that is coming from aliasing. Okay. Okay, that's the end of the section. Thank you.